How about this type of element? 0, 0, 1. Is it going to be in B union C? Okay. So these are elements. Okay, stop this thing, please. Enough. B union C, they will be, because these are elements that are not in B but in C. So they will be in B union C. Okay. How about the last row? These are not going to be, because these are elements not in B and not in C. These will not be in B union C. So we can populate this column, right? Next thing, we will populate A intersection C, A intersection with B union C column, right? What will that be? It will basically be the intersection of the first column. Well, there is no intersection between columns, but it will be, if I know an element is not in A and that element is not in B union C, then should it be in the intersection of the two, right? This type of analysis we will do. So these are elements in A intersection B union C. This is how the element would look like. And now we do A intersection B and A intersection C. This is easy. We know what is each element, which is whether it's in A or B, and based on that we will define whether they are in the intersection or not, right? So next we will take the union between these two columns, and you know what do I mean by this? That take the union between these two columns, and now observe that this membership for all types of element, the membership is column here and the membership column here are exactly the same. That means any of these 8 type of elements is either in both of them, it's 1 1, or it is in neither of them, it's 0 0. That means the if and only if condition for x in the left side is equal to if and only if x is in the right side set, right? So these are if and only if condition is true, and I proved it for all types of element, right? So for all x, I can't really go, depending on what's the universal set, I can't go to every type of every element, but I can cover all of them by just arguing generally about them by each type of those things. Okay. So similarly, the next thing, using membership table, A minus C union B minus C is equal to A union B minus C, right? 8 types of element, because 3 elements, 3 sets are involved. So an element could be any of these 3 types, 8 types, and then we can populate the table. Okay, this I hope you can do it very quickly. Okay, so another definition, another way to prove 2 sets to be equal is by using by logical equivalence of their membership predicates. Okay, so remember this thing, any element that is in X is in A, that's a predicate, and X is in B, that's a predicate. If I have to establish a if and only if between them. So X is in A, I will say whenever X is in A, this predicate is true, then X in B is also true, and whenever X in A is false, then X in B is false, right? So I will establish the equivalence between the 2 membership predicates, right? And from this we will conclude that the set A is equal to the set B. Okay. So let's just give an example with logical equivalence of the membership predicate actually. So this will prove your logical equivalence that A intersection B union C is equal to A intersection B union A intersection C. Okay. So let's say there is an element that is in A, not that is in, so X in A intersection B union C, that's a sentence, right? This is a predicate, maybe true or maybe false, right? I'll say that this predicate is equal to the predicate that X is in this set, the one given on the right hand side. Okay. So what does X in A intersection B union C means? Now apply the definition of intersection. This means that X is either in A, X is in A and X is in B union C, right? That's the definition of intersection, if you remember, right? Intersection is the set of those elements that are in A and that are in B also, right? X in A, X and X in B. If this predicate is true, then that element is in A intersection B. Okay. So here in this case, this state sentence is exactly logically equivalent to this sentence. Does anyone have any issue with this? X is in A and X is in B union C, right? Now, let's apply the definition of intersection here, union here. What does it mean, X is in B union C? X is in B, that's not the correct sentence. X is in B? No, X is in B or C. Give me a logical, grammatically correct sentence for this. Yeah, X is in B or logical or X is in C, right? X is in B or X is in C. So this is the definition of union. I just applied the definition of union. I'm rewriting exactly the same sentence, right? Equivalently rewriting it. Is this clear? Okay. So now this I have two predicates, three predicates actually. There is a predicate and then and with the or of two other predicates. What can I use? I can apply the distributive law of and over or. Yes, I know that this is always P and Q or R is equal to P and Q or P and R, right? That's a distributive law of logical operators, right? So from this I can write that this means that X is in A or X is in B and X is in B or X is in A and X is in C. Does this make sense? Yes? What is this? What is this sentence? Can you write this in more set notation? What is A intersection B? That's not even a sentence, right? Make a proposition, make a predicate. A intersection B is a thing, right? It's not a sentence. X is in A intersection B, that's the first half of it, right? X is in A intersection B, that's this the sentence. And the second half of it is X is in or X belongs to A intersection C, right? This is what I can just write by the definition of intersection. Yes? Now look at this. I will now apply the definition of union. What does this mean? X is in A intersection B, X is in a set P and X is in a set or X is in a set Q. What does it mean? X is in the union of P and Q, right? That's exactly the definition of union. X is in, does this make sense? What is this thing that I get? This is a predicate, or you can think of it as a membership predicate of the set given on the left hand side, right hand side. Is it true? Where did we begin with? The membership predicate for the set on the left hand side. So we said that statement X is in the left hand side set is equal to, is logically equal to, is exactly the rephrasing of this statement that X is in the set on the right hand side. What does it mean? The right hand side set is equal to the left hand side set. If this is true, then this is true. If this is false, then this is false. These are logically equivalent statements, right? The truth values will be equal. Does it make sense? Okay. So this is how we prove two sets are equal. Yet another way to prove sets being equal is, we saw this earlier. If yes, please.
So in the last proof that we just did, would we also have to do the other way around?
No, equivalence is commutative. If P is equal to Q, then logically equal to Q, then Q is logically equal to P. So they are equal statements.
But technically, haven't we just showed that X is in the left hand side and the right hand side?
No, we said we never proved X is in there or not in there in either of them. We just said the sentence that X is in the left hand side set is logically equivalent to the statement that X is in the right hand side set. They are logically equal, meaning if one is true, the other is true, and if one is false, the other is false. And that's what we never proved anything to be in a set or not in a set. Okay? Yes? Okay. So the next definition, and this is a very clear definition of sets to be equal, and this is what is most widely used in practice, that two sets are equal. We say that R is equal to another set S if R is a subset of S and S is also a subset of R. Okay? R is a subset of S means whatever element is in R are also in S. And S subset of R means any element that is in S is also in R. I mean, if you really think about it for like 5 seconds, you understand that that's basically another way of saying the set R is equal to the set S, right? Whoever is in R is also in S, whoever is in S is also in R. That means R and S are equal, right? Yes? Okay. So we'll use this definition to prove, and this I told you earlier that you can just see that because equality requires the if and only if between the membership predicate, X is in R, if and only if X is in S. And subset means X is in R, if X is in R, then X is in S, that means R is a subset of S. And S subset of R means if X is in S, then X is in R. If you combine those two implications, you get the by implication. Okay. So let's just prove this thing, and you're going to get but pay attention to this thing. Okay. The intersection of A union, the complement of A union C intersection B is equal to B complement union C complement intersection A complement. Okay. So looks like it's true, right? It seems to be an application of the distributive law and the De Morgan's law, right? But let's see, I'm going to prove that what this set on the left hand side is actually a subset of the right hand side, and then we'll prove that the set given on the right hand side is actually a subset of the set given on the left hand side. Okay. So this is what I'm going to use this strategy to prove that these two statements are equal. So I'm going to instead prove these two these two substatements. So first I will prove that the set on the left hand side is actually a subset of the set on the right hand side. Okay, that's what's given. This is what we call 1. Second, I will show that the set on the right hand side is the subset of the set on the left hand side. Okay, it's clear? Is everyone convinced that this will prove the equality? Okay. So let's just do, again, this is, the whole course is actually nothing but this is it's not even the optimal or something. It's like just application of definition, right? Just rephrasing stuff in a more conducive way for the given problem. And all of this the whole course is going to be like this. You have to be able to say stuff clearly and then actually use it clearly and try to do with efficient use of language is actually what's going to get you through this course. Let's prove one. Okay. You'll do it together. It's your in-class problem. To prove one, what do I mean? What is the definition of one asked me to prove a subset relation between two sets, right? What does it mean? Just substitute the definition of subset. What do we get? I want to prove. Is there anything here? So the left side set, I will call it P, okay, or L. L is better, right? Because I will not forget it's left. The left hand side set, I will just call it L, and the right hand side set, I will call R, capital R. Okay. So I want to prove L is a subset of R. Just rephrase it. It means I want to prove that if, for all x, if x is in L, then x is in R. Yes? If x is in L, then x is in R. I don't know if x is in L is true or x is in L is false, or x in R is true or x in R is false. I am going to just establish this implication, right? That this implication is true for all x. So how would you prove that? If x is in L, then x is in R. So what does this mean for x to be in L? This is x is in L. Just rephrase it or just expand it. Just talk a little bit more about it. Just in some different words, just write it. What does it mean x is in A, in the complement of A union C intersection B? What does it mean? Just apply the definition of complement. It means that x is not in some set, right? Yes? That means x is not in A union C intersection B. That's just the definition of complement. Does it make sense? Again, nothing there, no invention, no theory, nothing. Just rephrasing with applying the definition of complement. Okay? So now when I say x is in something, intersection something, if I just elaborate more about it, applying the definition of intersection, what do I get? what do I get? X is in this thing and this thing, intersection this thing. So I get two statement that X is X is not in something, intersection something. What does it mean? X is not in P intersection Q. What does it mean? Just restate it. X is not in P intersection Q. X is not in P and X is not in Q.
It's not in one or not in
X is not in P or not
X is not in P. Yes. X is not in P or X is not in Q, not and. Okay, intersection, it didn't make it to intersection, maybe because it was missing in from one of them or both of them, right? So X is not in P or X is not in Q, right? So here I'm saying when X is not in the intersection of these two sets, so either X is not in B or X is not in A union C. This makes sense? Just rephrasing. Now, if X is not in B, what do we mean? What do we know? Apply the definition of complement. That means X is in B complement, right? X is not in B means X is in B complement. Yes, please.
So what if X is not in both A union C?
Yeah, maybe both. So this is the logical or that could be both of them could be true, right? I'm going to prove in both cases X is in the right hand side set. Okay, so X is not in B means what? X is in B complement. Yes, that's again the definition of complement. When X is in B complement, what does it mean? X is in B complement union anything, right? Union any other set. That's again the definition of union in OR, right? So that means X is in B complement union. What set would I like? I will just write exactly the set I need here, right? Yes. दूसरा वाला कौन सा? Okay, so if X is in some set P, then can I say that X is in P union Z? It's true, right? X is in P union Z. That's the definition of union. Yes?
Then why is it the union negation of C and A?
Oh, because I want to look, don't forget, it's a good question. Why am I going in this direction? I could have rephrased it in many different ways. I'm rephrasing it because I'm making, generally we talk about X in, right? Why would I rephrase it? X is not in complement of this, right? The reason I'm going it because I want to get this statement, X is in this thing. I want to kind of translate this into what I need on the right hand side, right? So that's why I needed B complement. I said, okay, B complement is there. It's tricky. It requires practice. You have to do all of these. The previous examples we did through other methods. You should do it through this method. They are both. If two sets are equal, then one is a subset of the other and the other is a subset of the first one. That's always true. You should be able to do it, okay? You have to do practice with this. Yes? I want to use this thing. We said that we want to use this methodology. करने को तो हम बहुत तरीके से कर सकते हैं. We have other methods and we did 3 methods so far, right? We can prove the logical equivalence of their predicates. We can use the membership table. We can use De Morgan's law like you suggested or distributive law depending on whatever is needed, right? We want now a practice with this 4th method, okay? So forget about what we want. I just want to prove this one statement, the statement number 1, right? That what did we call? L is a subset of R. I'm just proving that thing. L is a subset of R. So now I will make a subset. So the question was, why did from here we went to this thing? Why didn't I use some other set Z here? Well, that's because I want actually a statement that if X is in L, then X is in R. So I would like something closer to R, right? True, I cannot just make up stuff, but it has to be true statement. So instead of any other Z, I will choose this specific set, C complement intersection A complement. Yes? So I got this thing. If either this is the case or this is the case or both. So if this is the case, I'm done. I proved that if X is in L, then X is in R. Okay? So let's do what if the other thing is the case, right? Yes?
ये हमने कैसे निकाला है? X is belongs to B bar इसके नीचे वाली लाइन जो भी.
Yeah, so if X is in some set B bar, then B complement. If X is in B complement, then X is in B complement union Z for any set Z. Isn't that the definition of union?
हमने बाद में extra लगा दी उसको union.
No, but I'm saying यहाँ भी वो Z is the extra ना. X is in some set P. Then can I say that X is in P union Z? Yes? So P is B complement. And instead of Z, I would like, because I want to make a statement that X is in R, so I will try to make it R. So Z I will choose such that it becomes R, right? So X is in B complement union C complement intersection A. So in one case, I established that if X is in L, then X is in R, only in one case, right? So we have to do the other case. What if that is not the case? What if X is actually in B? Right? What if X is in B, but because of this it was thrown out of the intersection, right? So let's say if X is not in A union C, again by definition, what do we know? What does it mean X is not in A intersection C, A union C? What does it mean X is not in A union C? X is not in A and X is not in C, right? Remember, because it must be in neither of them, that's why it couldn't make it to the union, right? So that means X is in A, X is not in A, and X is not in C. Apply the definition of in complement. That means X is in A complement and X is in C complement. Make sense? Yes? Now again, if X is in P, then X is in P union Z. What should be Z in this case? X is in B complement union. I would say that, okay, if X is in A complement intersection C complement, then X is in B complement union A complement intersection C complement. One of these statements must be true. Is it true? Or, there is an or between them. We have established that X is not in the union, so X must be missing from at least one of them. So in at least one of these two cases must happen, and in each one of them I prove that I'm happy. Okay, so now I prove the second side, which I want to prove that R is a subset of L. R is a subset of L, and that is just apply the definition of R. It says if X is in R, then X is in L, right? So if X is in R, then X is in L. Let's see, what does it mean when I say X is in R? When I say X is in B complement union C complement intersection A complement, what does it mean? Apply the definition of the union. What do we get? X is in B complement or X is in C complement intersection A complement, right? So at least one of these two cases must be true, right? At least one of these two scenarios must show themselves, right? One of these two. So now what do we do? If X is in B complement, then what do I know? Apply the definition of complement, then that means X is not in B, right? If X is not in B, that means X is not in B intersection anything, right? If X is not in B, then X is not in B intersection Z, it is not in B intersection P, it is not in B intersection Q. That's the definition of intersection, okay? So if X is not in something, then X is in the complement, right? And that's what I want. That's exactly what's given in the this side, right? This is the set what I want. Again, you have to go and work these out in detail later. Okay, the other case, if X is in C complement intersection A complement, if X is in C complement intersection A complement, that means by definition of complement and intersection, it means X is in not in C and X is not in A, right? That's the definition of intersection and complement both used simultaneously. That means X is in C union, X is not in C union A. X is not in C, X is not in A means X is not in C union A. Okay, definition of union or union. And X is not in C union A means X is in the complement of C union A. right? So if X is in the complement of C union A, then X is also in C union A. If X is not in, okay, if X is not in C union A, then X is not in C union A intersection B, X is not in C union A intersection P or Q, whatever, right? You can just again do this thing by definition of union. If X is not in one set, then X is not in the intersection of that set with any other set, okay? And that means X is in the complement of this set. If X is not in the set, then X must be in the complement of that set, and this is also what we actually wanted to prove. This session was about proving two sets to be equal. We can prove it using logical laws, set identities, set laws. We can prove it using set membership tables. We can prove it using the logical equivalence of the membership predicates, and we can prove it using the subset relation between both sides. Okay. So next, I'm just going to give you a few some tricks, some computer science tricks. The purpose of this in the next session, this is, I'm going to finish it quickly, is only to give you enough familiarity with this terminology so you don't get scared when people use these words with you. Okay, these are very, very simple concepts, some basic tricks of the trade. So, but I just want you to be familiar with them. Okay, so if I'm going to set, we can set as unordered collection of objects. Okay, unordered collection of objects. If I'm going to save them in a computer in this unordered way, unordered fashion, then making these set operations, doing the set operations are going to be very complicated and very complex. Okay, and these set operations are done significantly. These are the operations in database, right? When we are dealing with data, we take union of Zambil data with the admissions data, we take the sports data and take the union with the society's data and intersection with them, complement of them, find me all of these query processing, find me the top 10% scorers in a particular course. Find me the highest GPA people. This is all data operations, right? Find those people who have not completed their required courses. Find those people who have failed their prerequisite courses. And all these data operations are just sets and unions and intersection and complements and set differences and all this. They are going to be very complicated. We are going to do relations in in next week, and you will see that that's relational database is just building upon these sets operation. Okay. So these are computationally expensive, right? So, but typically if the universal set is not very big, right, if the cardinality of U isn't very big, then we can do the following, right? We can impose a fixed order on the elements of U and represent each element by a bit, just a bit, each set member by a bit. If it's 0, it means it is not an element of the set, and if it's 1, then it means it's an element of the set. So suppose my universal set is these things, 1, 2, 3, 4, 5, 6, these 6 elements, that's all my universal set. I fix this order. And now any set which is actually a subset of this U can be represented by a bit vector or a bit array of length 6, right, where there is a correspondence between each element of this thing. So let me just do an example. So this is my universal set and this is the fixed order. This is how I will represent a set. If I want to represent the set calc, chem and physics, I will just use a 6-bit vector, an array of length 6 of bits, where the first bit will be 0. What does this mean that the first bit is 0? Huh? Which element? DM is not an element of the set, right? The second bit is 1, that means calc is an element of the set, right? The third element is 1, the third bit is 1, that means the third element in the order. Now when I impose an order, then I can say the third and the fourth and the fifth, right? On sets I can never say give me the fifth element of the set. What is the fifth element of the set? Sets are unordered objects. There is nothing called the fifth element of a set, right? Or the first one or the last one. These things are ordered words, right? These are words requiring a known order. Sets have no order. But when I impose this arbitrary order, it's any arbitrary order you want, right? There is nothing No, it's not that some ordering is good than other order, right? You can choose a random order, you can choose any arbitrary order, right? Or you can choose just lexicographic order, or order by difficulties, order by quality, order by whatever you want, okay, in this depending on the whatever the case is. The third bit is 1 because chem is an element of the set. The fourth bit is 0 because bio isn't an element, and the fifth because physics is there and programming isn't there. Is this clear? So this is called the bit vector representation of a set. It's also called the characteristic vector of a set. Okay, the characteristic vector of a set. What will be this set? Quickly. What will be this set? Why is the first bit 1? Quickly say it. What will be this set? So why? What will be the set? 1 1 0 0 1 1. Does everyone know how many ones will be there in the bit vector representation of any set? The cardinality of the set. Depending on what is the cardinality of set, that's how many ones will be there, right? How many zeros will be there?
Size minus cardinality. The size of the bit.
What is size? The bit, the vector length? Okay. Yeah, so that's okay. So the universal set minus the cardinality of the set. Actually, the cardinality of the complement. Yes? Yep, okay. Is it clear? What will be the characteristic vector of this set? Quickly, this is now your ICP. For in this particular universal set, what will be the characteristic vector of the set chem and DM? Quickly, say it, and write it. 1 1 1 0 1 0 0 0. You cannot just say 1 0 1. Okay, that's not good enough. 1 0 1 is not a complete description of the set. It has to be 6 length bit vectors. Okay? Yes? Okay. 1 0 1 0 0 0. Okay, that will be this vector set. What will be this set?
All ones.
1 1 1 1 1 1, right? Because that is all 6 elements are present. The number of ones will be equal to the cardinality of the set. This cardinality is 6, so there will be 6 ones in the bit vector. Okay? What will be this set? DM and programming, because I am just establishing like this is actually the same thing spoken about in different words, right? Different. Now it's DM programming. What will be this set? The empty set, right? This is the empty set. It's a well-defined set. There must be a good representation for it. Okay. What will be this set? This is your ICP. So you know this is just a different way of representing a set, right? Some different way. Why do we do it? It's a more computational way of it. When the universal set is small, we use arrays, bit vectors. Otherwise, we use what's called key value pairs or other data structures. There is sets data structure, and then there are dictionary and many other things. What is A union B? It's a set of those elements that are in A or in B, right? The logical A. In terms of bit vector representation, it will be the bitwise OR of the two sets. This makes sense? Bitwise OR, you just say, you ask, is this element here? Is this element which correspond to, what was the third element? So, does it make sense? The bitwise OR makes sense? Why would I take the OR of 0 and 1? This 0 and 1, it means either this element, whatever the first element is, the first element of the universal set is either in A or in B. So, that OR, I will just apply OR and it will come 1 because it should be in the union, right? When will it not be in the union? When it is 0 in both of them. When this is not in A or in B, so the bitwise OR will give me 0, and that means that element will not be in the union, right? So, union is now the bitwise OR of the bit vector. Okay, the characteristic vector. What will be intersection? It will be the bitwise AND of the characteristic vector, right? Now you see, I told you this union intersection, we perform it very extensively, very frequently, depending on the database. If you represent them with bit vector, these are very quick operations. Bitwise AND and OR are preliminary elementary operations in any programming language. right? In any computer architecture, the union and intersection are not elementary operations. Your ALU, the arithmetic logic unit, doesn't do union and intersection, right? It does do, the ALU always does, what is it called, the union, and or and not and addition, multiplication. They does it very frequently. There is circuitry for that. What will be the exclusive OR? Bitwise exclusive OR, right? No, sorry, what is it called? It's symmetric difference. In set we call it symmetric difference. It will be bitwise OR, right? Bitwise exclusive OR will give you the symmetric difference. And other operations you can just make build based on that. How would you compute the complement of a set using bitwise? Which bitwise operator will you use for complement to compute the bitwise not, right, or negation? Just apply the negation of this thing. This other one is also, the purpose is just to give you some, just so that you hear these words once at least. So if you read it in some paper or in some other book or some course, or you go to a talk and somebody is talking about it, you don't get scared of it, okay, and don't get impressed with big words. So a multiset is an unordered collection. What is a set? An unordered collection of objects. This is an unordered collection of objects with repetitions allowed, right, where we allow an element to be repeated multiple times. That's why it's called multiset, right? Here is an example. In sets we said these things are not allowed. This is still the set 1, 2, 3, right? You can write 2 19 million times, still will be one object, right? And here if you write it 1, 2, 3, 3 times, now this is a 3 2's in this set, right? Its multiplicity is allowed, repetitions matter now, okay? Here is a set CS100, 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 CS210, CS210, the multiset of the last names of all professors in LUMSx, right? So there may be 19 million Khans. These are now different people, right? Different objects. The repetitions are allowed now. Okay. So order of elements is still not significant. The next topic is going to be about ordered stuff, right? Still order is not important. Remember, when we impose this order, that was a very artificial order that we had to do it just for our convenience when we do computational, the bit vector representation. Sets are unordered collections, unordered structures. Order is not important. So 1, 2, 2, 3 is the same multiset as 2, 3, 1, 2. Why? How many 2's are there? 2 2's. How many 3's? 1, 3. How many 1's? Only 1, 1. This is set, but if you write it in different order, they are the same multiset. Okay? But in terms of sets, they are different. In terms of set, this is actually the same set as 1, 2, 3. Right? But in multiset, these are different. So repetitions matter in multiset, multiplicity matter, and order doesn't matter. Okay? Okay, it's also called the bag. In some text, more computational text, they are called bags. Okay, bag of items, where you just put in stuff into bag. There is no order there, but you can put 2 apples and it's 2 apples, right? It's not 1 apple. Okay? Or sometimes it's written as M set also, multiset. Okay, the number of instances, the number of times an element is repeated is called its multiplicity or its frequency. Okay, frequency or multiplicity. More statistics, data science terminology is frequency, more mathematics, computational terminology is multiplicity. Okay, so just be familiar with the words and don't worry. Frequency also makes sense. How many times does it appear? How many times it is included, right? Now, this is because, again, this is just, I mean, giving an example, but this just follows from the definition. Okay, I have just 2 unique elements, 2 types of element A and B. I can make an infinitely many multisets out of it, right? How many different sets can I make from the universal set A, B? No, sets 3 or 4. Yes.
If we count an empty set.
If
We count an empty set.
yeah, so empty set. Why wouldn't you count empty set? Yeah, of course you'll count. Empty set is actually the best of the sets is always the empty set. You guys are just always be cruel to that. Empty set, the set containing the element A only, the set containing the element B, and the set containing both A and B. These are the four sets you can make out of it, right? It's called the power set of the set AB. Multiset, you can make infinitely many of them, because multiplicity is just an integer. You can just write as many times as you want. So, for example, here is a set AB, here is a set with 2 A's, 1 B, here is a set with 3 A's and 3 B's, and you can just take any number of A's, any number of B's, and you can write it will be different multisets. Okay? These are different multisets. Okay, 3 different multisets I give you, and you can make many. In terms of sets, they will be exactly one set. There is one set called AB, right, if they were set. Okay. So, generally how would I write sets? Now, how would I write M sets? This is not generally the way we write M sets, because if there are too many elements and too many repetition, it will just fill up the whole board, right? So, we need another notation for it. Typical notation for set is to write pairs, element, the object, and its multiplicity. Okay. So, for example, if you want to write this AA, BBB, one way to write it is, and that's a more standard way of doing it. Multiset are not very standard, they are not widely used, but occasionally are used in data science and computer science, and also mathematics literature and physics and many other things, but not very frequently, not very common. So, if you have 2 A's and 3 B's, you can write it as A, the object A followed by its multiplicity. So, it will be A and 2, and the object B followed by its multiplicity 3, right. The way it is pronounced is MAX, the multiplicity of x in A, right. X is multiplicity in A, x is frequency in A, right. That is how you can write this set 1, 2, 3, 2, 1 can be written as 1 followed by 1, 2, 2, 2 and 3, 1. Okay. I chose these numbers just so that you know that the first is an object, the first in this pair, the first thing is the object and the second thing is this multiplicity, right. So, this one is just a symbol, okay. This is just a symbol, it may be A or B or C. The other is a number, is an integer, okay. The third set Khan, Ali, Aisha is Aisha 1, Khan 2, Ali 2. That you can write in any order, right. These you can bring this Ali to the first place and Khan to the third place. That's exactly okay, as long as the frequency and the object is clear. Okay, it's just notation there. Some operations on this we are going to define. First of all, the support of A is, so there is a universal set and then there is a multiset. The support is actually those elements that actually appear in the set. Okay, so it's the set of those elements whose frequency or whose multiplicity is non-negative. Okay, so does it make sense? Okay, so this is the support. This is actually the underlying set. Actually, the underlying set. What's the set we are talking? So for this set A, the support is Aisha, Khan, and Ali. Right? Why is Ahmad not here? Because its frequency is 0, its multiplicity is 0, or maybe it's not even the universal set. Right? So only those sets that actually appear will be here in the multiset. Think about it. Your CD, do you know CDR, call data record? So suppose LUMSx has in their internet, LUMSx is doing some billing or for certain purposes recording who is. So this internet log, right? So they are maintaining a log. When you log in to the network, they record it somewhere. Does it make sense? If you save it as a set, what you cannot do? What type of questions you cannot answer? If you save the internet sign in log as a set, what is it that you cannot do?
Instead of what? As a set as compared to?
This is the set, yes. Okay, that's true. You cannot find out who is the most frequent user, right? Because you're not saying it's a set. Some people would log in once and now you have a daily record, you say, yes, this guy showed up and this guy didn't show up. But if you have it, save it as a multiset, you can say who's the most frequent user, right? Who is the most least frequent user, who otherwise it's just zeros and ones, right, in the other case. Okay, so that's the support and cardinality. So cardinality of set, those of you who are interested in that, cardinality is actually the sum of multiplicity. You add up all the multiplicity, you will get the cardinality. Okay, how many elements appear? So in this set, Aisha appear twice, Khan appear twice, and Ali appear once. So it's 2 plus 2 plus 1. That's the cardinality of this set. Okay. Okay. Some operations, again, it's kind of a subset, but it's called inclusion here. Inclusion of a set A is included in another set. M set A is included in M set B if the cardinality of every element of A, of the multiplicity of every element of A is less than or equal to the multiplicity of the corresponding element in B. Okay. So, for example, this A and B, I can say A is is included in B if, because the multiplicity of Aisha is 2, it's less than or equal to 3. The multiplicity of Khan is 2, is less than or equal to this 2, and the multiplicity of 1 is less than or equal to the multiplicity of Ali in the second set B, right? Is 1 is less than or equal to 2. For Imdad, it's 0 here and it's 1 here, so it's also less than. So A is included in B, right? This A is included in this B. Is B included in A?
No, because multiplicity from that is 0.
That's one thing, and also look at this, Aisha, 3 is less than or equal to 2 is not true. Yes? And that 1 is less than or equal to 0 is not true. Okay? So that's, in this case, it is not true. The union of two M sets is denoted by is A union B, and it's just you take all the elements that are in A or B, take the support of A and the support of B, take their union. But now it has to be a multiset. We need to add the multiplicity. For multiplicity, you take the maximum of the two multiplicities in either set. Okay? So you see, you just take all the elements in the support, you make this C, and you make their multiplicities of X is the max of the multiplicity of X in A and the multiplicity of X in B. Right? You take the max of those two. If an element doesn't appear in either of them, then you don't write. Zero multiplicity is not a thing, okay? It's not an element in the set of the multi. So what will be the union of this A and B? Aisha? 3, Khan 2, Ali 2, Imdad 1, right? That's because I just took all the elements and added them. How many? What is the support? 4 elements, and I took the max of the frequencies, corresponding frequencies. Okay. The intersection is exactly the same thing. I will take the support, I take the union of the supports, and then the multiplicity is the minimum of the two. Okay. So for what will be A intersection B here? For if A and B are these two M sets, Aisha 2, Ali 1, Khan 0, Khan will not appear, the minimum of the two, right? It will be the minimum of 0 and 2. So 0 we don't write, and Imdad we won't write. Okay. Again, this is just to make you familiar with this thing. Okay, and then there is a difference also. A minus B and B minus A. It's not commutative. A minus B is not the same as B minus A. All the previous operations are the same. Okay. Here you just write, take the difference of those elements, the multiplicities in A minus the multiplicities in B for those elements that are in A minus B. Okay. So in this case, you see Imdad is not going to appear. Khan will be 2 minus 0, and Aisha would be 5 minus 3, and Ali would be, Ali is not included because it's 1 minus 2, right? So I'll take the max with 0 and 1 minus 2. So 0 and 0 we don't write by convention. Okay. So this is not nothing wrong. This is just one thing I want you to hear, this word set of words. You know, when in computer science and in data science, in all of this, this is the beginning of this large language model stuff, right? Any large language model lecture will begin with this thing called set of words. You want to work with documents, you want to work with text, right? Now, computers generally are trained to work with vectors, right? And the mathematics is also just work with vectors, right? They work vectors are really cool objects, right? The text is a stupid thing. It's just. So we have a lot of linear algebra, a lot of other machinery developed for vectors, right? We say, okay, let's x be a point in n-dimensional space. It means it's a vector in the Rn, right? It's an n-dimensional array or whatever you call it. So there's something called vector space modeling. You get a text and you try to represent it as a vector, right? Just like we got a set and we represent it as a vector, right? The characteristic vector, the bit vector. So the set of the set of words model for text representation into a computer is actually the characteristic vector of the thing. You get a set, you get a vector, you define a bit vector of length, the size of your vocabulary, right? It's called sigma, the number of thing. And if a word appears in a document, you write 1 there. And if a word doesn't appear in the document, you write 0 there. Okay? So this is like the set of words representation of the book. These are words and these are books. This book is Antony appears, doesn't appear, Brutus appear here, Caesar appear in the 3rd place, Cleopatra, Mercy, Warsaw. Okay, my eyesight is just not working now. Is it clear to everyone? How do you represent a book or a text by a vector? That's what we saw earlier. For multiset, I told you the word for this is bag, right? The next model is called the bag of words model. Here the problem is 2 books can have a word, one book can have a word 19,000 times and the other book will have the word only 1 time. In terms of zeros and 1, they will look exactly the same, right? Just like I told you, one person would log in 19 times, another person log in once, and in terms of zeros and ones, you will not lose that information. The frequency information you will lose. So bag of words, you will not lose the frequency information. Rows may words, yeah, I guess, not set of words. And these are books. This is because I had this picture ready from some other by big data analytics course. Okay, so just wanted you to hear. The next word from here is what's called TF-IDF, term frequency, inverse document frequency. That actually takes into account frequency and it also takes into account rarity and importance of words. And the next word after that is called word to vec. How to represent words by vec? Word to vec is actually what's called representation learning, is now the tokenized, is actually the building block of because even TF-IDF, set of words, bag of words, all these models ignore the order of the words. They just say the word appear or not appear. How many times does it appear? How important is that word? Because the word the will appear in every document with very high frequency. But it's not really important because it appears in all the books, right? So that's why we divide with what's called inverse document frequencies, TF-IDF. You divide in, okay, in how many documents this word appear. If it appears in all, you will just slash its term frequency by a huge amount. But if it's very rare words, generally rare, but frequent in this word, the value will go up here and this word will begin to represent this document. But it doesn't take into account the order of the words. For order of the word, what's called a context, that is done through the word to vec model, right? A little bit deep learning, actually basic singular value decomposition from linear algebra. We are now beginning functions. We're just building upon, we're done with logic. Based on that, we built sets. Now we are going to expand our language, our vocabulary, our skills much more in this language. We talked about multisets. Now we're going to do functions, then relations, and then come back to back logic proofs, and then sequence and sums and other stuff. Okay. Okay. Look at the slides, the terms here. Which of these words have you heard? Have you heard the word Cartesian product, Cartesian plane? Have you heard the word functions? Okay, composition of functions. Okay, inverse of functions. Okay, we're going to go very quickly on this stuff. Okay, an ordered n tuple is an ordered collection of n objects. Ordered collection of n objects. You see sets, no repetitions, no order. Well, we kind of got rid of the repetition restriction, right, by introducing M sets, by allowing ourselves to count things multiple times. But order was still a problem, right? Let's do it with, now we expand our language and we start talking about ordered collection of objects, right? The notation is this thing, unlike sets, rather than curly braces, we are using parentheses, okay? Unlike sets, order matter, repetition matter. Does repetition, should it matter or not? What's like the more mechanical way, right from this slides, it should tell you repetitions should matter. It's very mechanical thing, not from background knowledge or from other thing. Just look at this slides, just the words. Why should repetition matters in order n tuple?
n tuple मतलब उसकी length n होगी तो repetition pattern.
Okay, that's a good thing. N tuple mean there should be n length, right? So if you have written something twice, it should be counted as two things. Otherwise, you won't be able to make up n, right? Other things, ordered also is going to tell us that repetition, because there is not two, we cannot say there are two b's there. There is the first b and then there is a second b, right? It's an ordered thing. Now those elements are different. There is the first appearance of that element, the second appearance of that element, the last appearance, the second to last, and the third one, and the fifth one, and so on, right? Okay, these are more close to generally arrays that we use in programming languages, right? Because in arrays are ordered collections, right? You can't just say that, okay, at the fifth position, this number is written, in the seventh position, you can't just reorder them. There is an importance there of everything. But generally speaking, programming languages, C++, Java arrays are supposed to be of a single type of elements, right? All integers or all doubles or all characters, all floats, all bits or whatever, right? This type restriction isn't here, okay? So everyone knows what is an ordered n tuple? Okay, it's an ordered collection of n objects. The notation is write those n objects in whatever order you want, in whatever order you mean, and add it in parentheses. So order matters and repetitions also matter. Okay, so two ordered n tuples are said to be equal, not that if they have the same items. They have to have the same items, the same objects at the same location, at the corresponding locations, right? So two n tuples are equal if the first element of the first tuple is the same as the first element of the. So two ordered tuple A, let's call it capital A and capital B. A will be equal to B if A1 is equal to B1, A2 is equal to B2, A3 is equal to B3, and so on, right? So now we say for all I, AI is equal to BI. For all I between 1 and n, AI is equal to BI, then those two things are equal. So for example, this 129 is equal to 129, right? One Apple 8 car is not equal to one Apple car 8. Why? Order is different, right? Or you can see that the third element in the left side ordered tuple, order 4 tuple is 8, and the third element in the right side order tuple is car, and they are not the same. They are not equal. Okay. 357 is not the same as 35711. So look at this thing. Look at this question. How many elements are here in this 4 tuple? How many elements are here in the 4 tuple? Let's say they are sets. Let's say they are sets. So how many elements will be in the left set? What will be the cardinality of the left set? What will be the cardinality of the right set? Are these equal sets? Are they equal sets? Why are they equal? No, cardinality is not the elements are also the same, but in different order. Are they the same in terms if they were 4 tuples? Ordered 4 tuples, they are not the same. So order matter, right? In whatever order you write or you list them, that's very important. Okay, these are ordered tuples. 357 is not equal to 35711. Why?
They have different lengths.
They have different, don't use other
Three
words.
tuple
No.
and four tuple.
One is a 3 tuple, the other is a 4 tuple, so it's not even a question, right? It's like an invalid question. 35711, 37511, are they equal? Why not? Because the second item, the second object in the left hand side is 5 and the second object in the right hand side is 7. They are not equal, that's why these two are not equal, right? How about these 3557, 357? One is 4 tuple, the other is ordered 3 tuple, right? 3557, 3575. Both are 4 tuples because their order is different. By the way, in both all of the three, if they were sets, they will all these three will be equal, right? Generally speaking, XA is not equal to AX in general. Okay, just keep that in mind. Ordered is important, so it's an ordered pairs, ordered collection. Okay, when n is 2, ordered n tuples are generally called ordered pairs. Okay, ordered pairs. We call them ordered pair. Ordered 2 tuples is too hard to pronounce, so we write it ordered pair. Okay, n equals 2. The Cartesian, this is what the actual topic is. Cartesian product of two sets A and B, again this is now an ordered thing, is the set of all ordered pairs xy, where the first coordinate, the first element of the ordered pair comes from A and the second pair, the second element, the second coordinate comes from B. Okay. Now we can talk about coordinate and other stuff because we have indexing, right? We have a proper order there. So A cross B is all ordered pairs xy where x comes from A and y comes from B. xy such that x is in A and y is in B. The second element comes from B, the first element comes from x. Okay. It's also called cross product or the Cartesian product. Okay. Here is an example. Let's say S is x1, x2, x3 and G is A, B, right? What is the cross product? What is S cross G? x1 combined with A and B, x2 combined with A and B, x3 not combined, but okay, so combined with, paired with, yes, very good, yeah. So x3 paired with A and B, right? That's the set of all ordered pairs that takes the first coordinate from A and the second coordinate from B will give us A cross B. Okay, the cross product or the, you must have heard this word R squared, right? This is called the Cartesian plane, R squared, or it's R cross R, right? When we draw it, the Cartesian plane or the 2D plane, right? It's R cross R. It's actually the Cartesian product, the set of all points where the first is also the first coordinate is a real number, what we call the horizontal axis or the x-axis is a real number, and the second coordinate is also a real number. So all 2D vectors are, all possible 2D real vectors are actually is called R squared. It's a Cartesian plane or something like that. Yes, ordered pairs are ordered 2 tuples, but when 2 is fixed, then we say ordered pairs, right? So ordered 2 tuples, a set of all ordered 2 tuples that can be made from between A and B is going to be. What if I write x1a here and x2b there and x3b here? It's a set. No matter how you write, there is nothing, no order there, right? You have to take all the ordered pairs and write it. In whatever order, it's a set, no order there. So, can I say that this point is before this point? No, there's nothing called before into this thing, right? Is it before? Is it the first point or is it the set point? This is a set. It's a set of points. What is the cardinality of this set? It's infinite, right? And what is the type of each element in this set? It's an ordered pair. It's 2 numbers, 2 real numbers, right? In fixed order, right? That's why some of you said that you heard it as a solution to system of equations, right? That's why that's the solution to system of equations. It's a two lines and where they intersect, or two functions where they intersect, that will give you a point here if they do, and that will be the solution to the system. Remember, it's a set. This order is not important. Within a pair, the order is extremely important. It's a set of ordered pairs. Okay, it's an unordered collection of ordered pairs. Okay, now you can write x1b 19 million times, it will still be just x1b. Okay, here is some more example. X is the set containing two numbers, two elements a1 and 2, and y is the set containing three letters a, b, c. X cross y is 1a, 1b, 1c, 2a, 2b, 2c. Y cross x is a1, a2, b1, b2, c1, c2, right? Are they the same? They are not the same. Why is it not the same? This one a1 is not equal to 1a. a1 is equal to 1a? No, because it's an ordered pair. The first element here is a, the first element there is 1. They are not the same. Okay? What is x cross x? I said Cartesian product is defined from two sets, right? So, what if the sets repeat? What if the same set? What is the Cartesian product of a set with itself, right? What is x cross x? It's a set of all ordered pairs. Just plug in the definition. The set of all ordered pairs A, B, P, Q, where P is from x and Q is from x, right? So, this will give us, what is x 1 2? It will give us 1 1, 1 2, 2 2, 2 1, right? 2 2 2 1, that is the set of ordered pairs. Now, you can write this 1 1 1 2, or you can write it 1 1. Okay, so you can write in pairs in different order, but a pair has to be internally, it has to be in order. Okay, is it clear? What will be x cross empty set? I told you empty set is a very important set. Cartesian product is defined for sets, right? There is a set A, there is a set B, and I can take their Cartesian product. What if the set B, A is equal to x and the set B is the Cartesian product of x with an empty set? What will that be? The set of all ordered pairs where the first coordinate comes from x and the second coordinate should come from the empty set, right? So, how many ordered pairs are there? Or just give me any element. You take all elements of x and pair it with nothing. How many pairs do you get? You see, no pairs, right? You don't get any pairs. Yes? Empty set cross x. You take all elements of x, write them as a second coordinate, and as the first coordinate you write elements of the empty set. How many teams will you get? How many pairs will you get? Nothing, right? You will not get any pair, you will be 0, so it will be an empty set. Generally speaking, is A cross B equal to B cross A? You see, x cross y is something and y cross x is totally different, they are not the same. But I can show you an example on the board. X cross the empty set is empty set, and empty set cross x is also empty set, so they are equal. One example, one counter example, or one example does not make proof. So, generally speaking, they are not true. Here is another example here on the board. X cross x is 1 1 1 1 1. Suppose I write x cross x, where I mean the first x is the second x. It will be exactly the same. So, generally speaking, x cross y is not the same as y cross x, unless x or y, A or B, one of them is empty or they are actually the same, right? If they are the same sets, then you may get that they are their ordered product, their cross product is the same, or if one of them is empty or both of them are empty. Okay? Okay, happy? Yeah. So, it is very easy to generalize them, define Cartesian product of more than 3 sets, just like you kept on asking 3D space. We talked about R cubed, the x axis and the y axis and the z axis, those type of points, 3D vector. What will be the Cartesian product of A cross B? It is denoted as A cross B cross C. What will that be? A cross B cross C. What will be? It will be the set of ordered triples, right? Ordered triples or the 3 tuples, where the first coordinate comes from A, the second coordinate should come from B, the third coordinate should come from C. It's denoted as A cross B cross C, right? In this order, the first has to be from A, the second has to be from B, the third has to be from C. A cross B cross C is not the same as B cross A cross C, okay? So, what will be the A cross B cross C? P I4, Pi5, Pi6, Pj4, Pj5, Pj6, Qi4, Qi5, Qi6, Qj4, Qj5, Qj6. Okay. So, generally speaking, we talk about this stuff a lot when we do combinatorics. The cardinality of Cartesian product of n sets is the product of the cardinalities of each set. Okay. So, the cardinality of how many elements are here? How many? 12. What is the product of A and what is the product of the cardinality of A, B and C's? 2 into 2 into 3, right? That should be 12. Okay. So, generally speaking, if you have n sets, you take their cross product, you will get the number of ordered n tuple you will get is product of the cardinalities. Okay. So, that is what we did so far. Functions. How many of you have heard of functions? Everyone should have seen functions, right? This high school math is essential subject, right? A function, suppose I am given two sets x and y, okay? A function f, okay, a function g, function h or something, so I just, it's good to give them name. A function f maps every element of x, a function f from x to y maps every element of x to exactly one element of y, okay? One element of x to exactly one element of y. Both these words are very important and we will see in a minute. So, suppose there is a set S and a set G, right? Suppose A stands for, the set S stands for students and the set G stands for G. If I want to say every student gets a grade, right? If you remember in the first session we talked about this thing, every student gets a grade. That is basically a statement, there is a function from S to G, okay? Now, every student must get a grade, it should be a function, and every student must get exactly one grade, it should be a function, right? If a student gets both A and B, what would you call it? It is not grading, right? If a student does not get a grade, what does it mean? It is not grading, right? It is something else. Anyway, forget about grading, but this is just an example. A function is a mapping, a function f maps every element of this S, it will map x1, x2, x3, x4, x5 to either A, B, C and F, right? Suppose some student got X grade, what would that mean? It is not a function, right? It has to be, suppose some student X19 also got a grade, it is not a function, right? It has to be these S and these G and exactly one and all of this thing, right? So, all of this stuff is included in this block, this stuff, you should know that. Here is a crazy idiot who just does this grading. What is this thing? It's like mechanically, syntactically, what does it look like? What is each object and what is this thing? Is it a ordered tuple or a, it's a set, right? It's a set. And set of what? Ordered tuples, right? Ordered pairs. What kind of ordered pairs? Where is the first coordinate and where is the second coordinate? The second coordinate is from S, the second coordinate is from G. It's actually a subset of S cross G. Yes? Everyone, it's a subset of S cross G. Now I'm going to give you in a minute what does it mean when a subset of S cross G is called a function and when it's called a relation and what is called some other things, we'll see those things, okay. So, this is the notation f, when you have a function from x to y, we write it as f, in LaTeX you will write f slash right arrow, slash maps to y, this will give you this thing. F of x is equal to y mean this x, because the definition says f maps each element. F of x equals y stands for this sentence that x is f maps this element x to this element y, where the y is in the set y and x is in the set x. Okay. This is how it is. We also say that y is assigned to x. X is mapped to y, y is assigned to x. Okay. Now, the requirement says that each x in x must be mapped to exactly one y in y, right? A given y, element y in the set y can be assigned to many, right? That's not just like previously, f was assigned to many students or a was assigned to many students, right? That's not important. Here, in this is a proper function even though b isn't assigned to anyone, right? This is a proper function even though f is not assigned to anyone, right? This is a proper function, nothing wrong with that. F could be assigned to many students, right? But a student cannot get multiple grades, but that's a function. So this is the restriction of, we said that a function, actually the way I wrote it is actually a subset of S cross G. So generally a function will be a subset of X cross Y, right? It will be a subset of X cross Y with the restriction though that in the ordered pairs, there must be exactly one ordered pair with the first coordinate as an element of x, right? A given element of x must appear exactly once as the first coordinate of the ordered pairs, right? Of some ordered pair. Okay, so how can we represent sets? That's one way to just to give you the list, right? The list of ordered pairs, the mapping and the element and its mapping, right? Where is it mapped? The other one is to draw what's called a bipartite graph. So I'll write on one side all elements, I will write all elements of x, the set S, in this case S, and I'll draw all elements of the set G, and if an element is mapped to another element of y, I'll draw a directed line between them, or I draw an arrow between them, right? So that one mapping where x1 was mapped to f, x2 was mapped to f, x3 was mapped to f, x4 was mapped to f, and x5 was mapped to f. This is one representation of a function. This another representation is draw S, draw G, and because x1 is mapped to f, I'll draw a line from x1 to f, right, a directed line. Because x5 is mapped to f, I will draw a line from x5 to f. Okay. Another that's more reasonable thing could be drawn like this. Okay. Does everyone know what a function is? Keep in mind ordered pairs definition, Cartesian product definition, and that function is a subset of Cartesian product with that restriction. Okay. We will now see some more examples and then we will go home and do the rest of the stuff tomorrow. Okay. Some terminology. F of x y, this is the way we write it. F of x is equal to y. Suppose some element x, a generic element x is y, right? F of x is y. The mapping x is mapped to y, or y is assigned to x. Okay. This set x is called the domain of f. The domain of f. The set y is called the codomain of y, of the function. X is called the pre-image of y. This element x is called the pre-image of y. And the element y is called the image of x, right, where it's mapped to. The range of f is the set of all images, right? So in this case, what is the domain? This set x, right? Where is the codomain? This set containing a, b, c, and f, right? This is the codomain. What is the image of what is the pre-image of c? What is the pre-image of a? The pre-images of a is x2 and a is x2 and x5, and what is the image of x1? What is the image of x2? What's the image of x2? x3. Okay, so you know what is the range of this set function? The range of this function is actually the set of images. Okay, one thing keep in mind, you can go home and for 30 seconds make up an example. Suppose LUMSx hostel allotment was a function, right? There is a set of student or hostelite student, and then there is a function and there is a room assignment. A function would mean nobody gets 2 rooms, yes, and it would also mean nobody sleeps on the street, right? Everybody gets exactly one room. It will also mean nobody gets a room in Gulberg, right? Because it has to be this Y, right? It will also mean no non-LUMS student should get a room. Yes? Yeah, because domain is the set of LUMS hostelized students. The codomain is the set of LUMS rooms available in the hostels, right? People can get the same room, right? You could be roommates, right? Okay. So some basic terminology that we established. So this is now this. Let's do with the same examples that we discussed. This is how we can make a function. This is how one representation. This is another representation. What is the range of this function? What is the range of this function? The set A, B, C, right? Because A is the image of 5 and 2, and B is the image of 3 and 4, and C is the image of x1. Why is F not in the range? Why is F not in the range? Because F is not the image of anything, right? And is F part of the codomain? Okay, so codomain and range are two different things. That's a very common confusion from these, some textbooks, I guess, write it or something. People commonly confuse this thing. Range is different than codomain. Okay, range is a subset of codomain. If it's equal to the codomain, then there is a different meaning to that.
So the codomain is the values it can take and the range.
Yeah, the codomain is the possible images and range is the actually used images. Okay, okay. Next question. What is the range of this function? What is the range of this function? What is the range of this function? The set containing f, right? Element f. What is the range of this function? Is it ABC? What's the range of this function? What is the range of this function? Is it ABC? Why is f not in the range? It is not a function. Range of a function, range is defined for function. This is not a function. Why is it not a function? Because x5, x3? Isn't this 3? F of x3 is b, right? Oh, here. Okay, so this is different. Okay, so x5 is not, x3 is not mapped, right? Every element of the domain must be mapped to exactly one element of this is not a function. Okay, so the range question is invalid, right? Look at this function. Is the range of this ABC? It is. It is not a function. Why? Homera, can you count them? How many? Why is this not a function? Because this is not mapped to, right? There is nothing. The moment you do this kind of draw two lines out of x4, you broke down the system, right? This is not a function, right? Every element of the domain must be mapped to exactly one element of the codomain, right? Here, x4, there is an attempt to make x4 map to more than one element of the codomain, okay? Okay. So when domains and codomains are large, we can describe function by some kind of formula, right? Some kind of mapping rules. Okay. We can also describe function with a mapping rule. Okay. We don't really have to explicitly tell you who is mapped to 1. I can just say those whose names start with A go to M1 and those whom names start with B go to their allocated rooms in M2 or something like this, right? Like for example, here's the grading rule. Typically we use something like this. If the score is between 80 and 90, they are mapped to A, right? So I don't have to, it's going to be very useful if the domains are very large. We can also describe, so you can go do this example for what is the domain or codomain of this function. This is how we are used to mapping rules from high school. This is another way of looking at functions. The function is, we can describe function, that's why the C++ and Java things are called function because of this thing, okay? Because it's actually a function. It takes an input, it gives an output. The input it takes is from some domain, the output it gives is from within some domain. And for a fixed input, the output is actually, we can think of it as a mapping, from that function. Is it clear? Think of it, this is a function, you can do all these kind of examples. Here is a summary, we will begin next time after this types of functions. Okay. Thank you.